one-to-one fit, like our computer model, okay, in the 3D case, the computer model is this, right, 3D volume, that it represented the lower picture of the three, right? And the middle picture was the forward model data, which we compared to the measured data. So that forward model data is what we calculated here, versus what we measured in the field. If it's one-to-one, then they fall along this diagonal, right? If they're not one-to-one, you see here's some noisy data. I likely need to remove that.
And how would you do that?
So it's extremely simple. You just come over here to view, you go to your misfit histogram. So are you familiar with histogram?
Yes.
Okay, so it's like a binning technique. So we take the relative misfit here and we say things that are below, let's say 9% misfit, they're on this side, right? There should be in here for like 4.5%, from 4.5 to 9%, 9 to 13.5, so forth, right? And if I can actually, you can see here the number of data. You see the blue line?
Right.
Anything that's red on the right side will actually be removed. That basically means data that is further away from this diagonal. Like if you imagine a parallel line to it.
Right.
As I move, so let's move this line over. Now you can see there's 81 data, but the contribution is so small that it doesn't even appear on the graph. But I can see it's here. If I keep going, I could guesstimate that to be, that's 6, 10, 20, 30, maybe 40. You know, I would come down, yeah, about there. I would remove the data. Like I said, it's very well fitted data.
So when you're moving it over right now, it's doing what? Eliminating those?
It's eliminating things that are far away from this diagonal.
Okay.
So anything that's not fit. This means that the measured apparent resistivity is much greater than the calculated resistivity.
Okay.
Right? Because if it's one-to-one, this data point would actually be up here.
Right. So that's something that misaligned and.
Yeah.
Okay.
So most likely what happened was not, there's not an issue, an error in the calculation. The error is here. The data point, this data point has to do with the voltage and current that we measure, right? So that means that the voltage was measured wrong.
And why would that happen?
You have noisy data.
Just something interfering.
Yeah, there's maybe another source of electric field, or the signal is very close to the noise, so it's hard to differentiate, But we're collecting 6,000 data points, so it's okay to lose 0.7% of the data set. Matter of fact, it's actually okay to lose a lot more than that, and you will have to just kind of expect that, because going out there, the possible number of combinations for 3D survey with 112 electrodes is up in the millions, and we're selecting 6,000 out of that to collect. Why? Because most of them can't be collected. For example, if I look back, if I look at this right here, let's see, if I have a dipole here, and like I'm transmitting here, and then my receiver's really far away over here, well, there's probably not a very good chance that I'm going to measure a good signal here if it's that small and that far away. But literally every combination can be made.
So what was being measured in this particular test or survey? What were they looking for?
They're looking for treasure.
Treasure. So the red
They're
spot.
looking for a cavity with treasure in it.
Okay, so the red spot was where it was found, or something.
That's where they dug a hole.
Oh, they dug a hole there.
They dug a hole into this thing which they thought was a cave.
Okay.
They manually dug it through the rock.
Wow.
I have pictures of people standing down in this hole. So, okay, so how do we look at a 3D? Do you see this electrode all the way out there? That's because it's a pole-pole survey. So they actually put one of the transmitter electrodes way out here and one of the receiver electrodes way over here. But you see, you get a very deep measurement, but it gets very low resolution here. All right, so now let's actually view this thing, because that's important to be able to understand. So we can do this dynamic slices like this. Rotate this around. We can click on here, see what the resistivity is down here. We have the resistivity in XYZ location. And we can also move these through. Depth-wise, we can rotate this. Rotate this view to look at it. Let's reduce the electrode size here. You can actually see better. you can also grab these, I believe, here and actually make a, select another plane through this section. Okay, so that's one way to look at it, right? Another easier way would be is if we go to here, or we go to inverted resistivity model like this, and then we come here, change the opacity. So right now I've only got 16 colors, but if I go and do, let's see here, let's remove all the conductive stuff. So I could draw like a color distribution that I want. But let's just, I'm gonna just try that, apply that, like this. Okay, here you actually see the shaft that they dug down. And then what this actually is a gypsum seam. Gypsum is well, you know what drywall is, right? That's gypsum.
Right.
So it's very dry, very resistive. Shows up as very resistive here. And of course, I'm deciding here where the contour I'm drawing, I know it's not that big. So after ground truthing, I know that it's actually smaller. So if I maybe go like that. There we go. So in this case, okay, if you're mining gypsum, this would be kind of interesting because you can come down here and say, all right, you got 22,000 cubic meters of material right here in this particular. Of course, this guy was looking for treasure. Of course, there was no cavity down there. So, but that's what people do.
Just out of curiosity, did they find something?
No.
No, they just found the hole and that's it?
No, they dug the hole because he thought there was, he thought there was a cavity around here somewhere. So he had us come do a measurement. So we found this resistive thing just like this. And it turned out like there was, there's nothing there. It's not a cave, it's actually just gypsum. Why he wanted to do it there, I have no idea. But usually these kind of legendary stories start like this. Well, I was sitting in a bar the other night and it was this old man with a map. And I paid him $20 for it. Usually how it starts. So I actually met this guy. I was young at the time.
Okay.
Yeah.
So,
but the thing is, for you, what we're looking at here is really about, once I get the data, how do I look at it, right? So
can I stop you right here for a minute? So, if we measure the resistivity of amber, we'll be able to color coordinate it on a 3D model like that, and it'll show up if there's a bunch of it there.
Yes, of course. I mean, that would be the ideal thing if there's a bunch. Is there a bunch, or is like little pieces everywhere? That's unknown because your process of getting it out, kind of just flooding it and mixing it up the sand and basically it's less dense, so it keeps moving up. It kind of disturbs and messes it all up, so you have no idea. You don't even know how much of it you're getting. Maybe you're only getting like 1% of everything down there.
Right, but if we know, for example, that it's 10 meters down and 10 on the X and 10 on the Y,
yes,
then we can excavate that
yes,
right there and pull it.
Yes, exactly.
Okay.
And that's the portion we call ground truthing. That's actually taking this data and then being able to verify what you found, and then be able to interpolate that information across the whole area, right? This is an important part about doing this kind of exploration, is that this data gives you electrical properties which tie into the structure, the different geologic units there. It also may actually directly target your amber, but I tell you, you're saying that it's in size maybe much smaller than that most of the time. But
it varies.
I would imagine this is one of your more impressive samples, so you can show, right? Because it's large.
No.
No?
No.
Okay. Well, in any case, I would say that at the depth that you want, 30 meters is deep.
I know.
Excavating down that deep is
No.
not even possible. I would say like 10 meter.
Right. The 30 meters is what feeding water down there. That's what's been done up to 30 meters.
Okay.
And like I said, majority of it is being found in the 15-20 range. which is doable. Excavating.
Excavating down there,
It-
15, that's like 45 feet, yeah.
Yeah.
You gotta really get, if it's unconsolidated and it's loose, then you gotta have like a pit that goes like this, right? Not a shaft.
Right.
Is that what you end up with?
They'll grade it and
Oh,
see
they
what.
just keep removing it or
Right.
bulldoze it over until you get down. Gotta remove a lot of volume.
I know, and that's
So
again.
this is actually part of your economics of this, is that removing that material, here you will be able to see how much material down that you're gonna have to remove to get to, and you can estimate the, because your bulldozer can remove a certain amount per hour.
Or the human labor. No kidding.
Or, yeah, no, it's true. It's just the problem with the human labor is you can't trust them.
Right.
Because if it's worth enough, they'll stick it up their ass to take it. With
Yeah.
You cannot stop them. They're gonna,
People do. I mean, some
yeah,
of the
and then,
things.
then they talk, they go home, they talk to their friends and family, suddenly it gets out there, and there's people that you would never want to mix with, are suddenly in your life,
Right.
and, these are other very dangerous situations. Anytime you do anything with value,
Right. It's
so,
absolutely.
you can't really even trust the people that you hire to protect you, because, they can be paid by somebody else too.
You're right. You're absolutely right.
So this kind of gives you an idea. This computer, I think it's got 8 gigabit or gigabyte of RAM. Maybe it's like a $800 computer.
Yeah. So I was just wanted to sure we don't.
It's a very low end computer.
Right. I wasn't like.
Maybe it's $500.
As long as we don't need like some super.
No. Okay, so we do a lot of CADing, computer aided design,
Mhm.
and that requires also a lot of RAM and speed. And so I bought a Dell computer for my machinist, and I think I spent $1,000 on it with 16 gigabyte of RAM, 8-core processor that was pretty fast. I mean,
Build it
$1,000.
yourself? Is that it?
No,
Off the
Just-
shelf?
yeah, called, checked on the Dell website. I think now that they've reorganized, they don't have all those options, but I mean, you can just go, if you build yourself, you just go to one of the computer manufacturers and you just buy it off the shelf.
Yeah.
In the range of $1,000 will actually go
Yeah.
pretty far.
It's not. Yeah.
10,000 will get you the best computer to do parallel processing. Oh, by the way, so this one is a very small data set. It would, if you were going to do 5 lines of 112 electrodes, this software is not going to do. We have a parallel processing code, the 64-bit, allows you to separate out the work on many different cores. It costs additional. I'm not sure if I quoted that to you, but the expense is something like maybe $7,000-8,000. And it comes with the 3D.
So
It comes with this as the visualizer for it.
I'm sorry. Back up. An additional parallel software that does what now?
So we have the Archimedes 2D, which is a 32-bit program. Then we have the Archimedes 3D, which you see here, which has all the visualization. It can do, 3D like this.
Okay.
It could do, 3-4 lines of 112 also. But you ran with 32-bit operating systems. You run out of available RAM.
Right.
Like if you put 4 gigabyte in there, Windows uses like 1. You can only use like 2 or 3 gigabyte. Even if you had 8, they would never use it.
Right.
Okay? So we developed a software that we call it Earth Imager 3D CL. It's command line. It's basically like runs off the DOS prompt. Well, we have like a little GUI for it. So you run it. Now you can run it on a server that can have several CPUs and many cores and take this enormous mathematical problem and kind of divide it up into all these different little cores to do this processing together, come back. That software is something like $7,000-8,000, but it also includes the 3D software.
Okay, because I thought you were talking about one seat license for the 2D and then $3,000 for another one, which is 2D and then the 3D. Is that what you're referring to?
That one's like around 7,000, 2D
Okay.
and 3D. So you gotta add like another, I'll look it up here in just a few minutes. But it's an additional cost. If you buy the whole package together, you're probably gonna be in the 8, 9. 7. I don't know. Let me
I
just
think,
look it up.
yeah, once we run through this whole thing and then have a chance to look at the equipment and how it operates, I think we'll pick and choose of which options and then build it from that point and move forward from there.
Yeah.
So go ahead, unless you wanted to do something else.
Well, this thing has a lot of capability. You know, you can do things like that. You know, estimate the volume. So if I make it opaque, right now I've got to kind of. Yeah, this software is designed not only to be good at, you know, modeling what you have, but also what it comes down to is you have a client, that's yourself or somebody else is paying for it. They want to know, I mean, you have to convey the information that you collected to something.
Mm-hmm.
We call this the turkey data set.
Mm.
But anyway, this is easy for anybody to understand, like, okay, so this is the target I have, and you know the volume of this area here is 22,000 cubic meters. And well, this might, yes in meters, okay. But you know, maybe they're looking for much smaller features within here. Let's go to another one. We'll read in this borehole.
So this software also used for like oil reserves and stuff like that? Do you do that, or is that not deep enough? It doesn't go deep enough. Because I mean, looking at that gypsum deposit, it would seem like an idea.
Okay, so you know, oil and gas is typically on several thousand feet,
okay,
right? Which would translate down to several kilometers. Sure, we could do it, but I mean, it would be very. First of all, from the surface, it's too far away from us, really. You know, we're good in the first, like for geotechnical purposes, the first 100 meters, we're excellent at. For mineral exploration, we're down to like 500 meters. For geothermal studies, we go down to over a kilometer. But they're looking for huge things. You know, when you're doing a geothermal study, you're not looking for like a little target. You're looking for a huge geothermal gradient. And of course, when rocks are melted, they actually become more resistant. You know, so. Okay, so.
You can get that if you need to. I mean.
No, that's fine.
Okay.
Yeah, so some of our clients will use, not for the oil exploration, but you know, right now we have this thing about global warming, and people are starting to realize that, you know, we're pumping a lot of carbon into the atmosphere, and that's, you know, traps heat, and so you have this kind of greenhouse effect. Well, they're talking about taking the CO2 that they get from oil wells, because you know, oil, it doesn't just come out oil. You get natural gas, you get all kinds of little things. You get CO2, all kinds of things. So they want to pump it back into old oil reservoirs that are underwater, like, you know, a mile or 1.5 kilometers. We delivered a system to Spain last year that they were doing, like, I think about 1,300 meters and 2 boreholes, cables. They're down there, and what they're doing is, while they're pumping in the CO2 into the ground in an old oil reservoir, they are monitoring how that moves throughout there. So it's kind of indirect thing. It's not looking for the oil. Now you're actually taking an old depleted oil field and you're pumping CO2 back into it.
How do they keep it from escaping?
Well, the same way that this high pressurized oil stayed there for millions of years. It's not
Just plug the hole?
Yeah, they plug the hole.
Okay.
Did plug it. I mean, it's rock. There's impermeable rock formations, like usually what's called shale. Now it's become very, and this is opens up another can of worms, because you hear about fracking, right? Well, what is fracking? Well, that is that when you have a reservoir, you typically have some kind of trap that keeps it from migrating further up, right? Because the oil is less dense. And that makes sense. Oil typically floats on water. Some hydrocarbons do, right? But anyway, it's less dense than rock. Shale is one of those impermeable membranes. So you have lots of gas, natural gas, over the oil that's trapped right there. You can't get it out, it's stuck in the shale. So what you do is you drill a hole through the shale and then frack it. You push water and chemicals into it at such a high pressure, it breaks open the shale and releases all this gas, and then you collect that. Before, we were going for the oil because that was the easiest thing, but now that we depleted a lot of oil, we have a lot of natural gas still stuck there. And so we're like, you know, it's become very economic to do that now with fracking.
Mm-hmm.
Of course, that's the impermeable membrane that keeps all the petroleum there. So you frack it, then it wants to continue up.
Mm-hmm.
So these are the things that people have, concerns about.
Okay.
So we're involved in that industry too, because there they need to know. For one thing is they need about 1 million to 10 million gallons of water per hole that they frack.
Wow.
That's a lot of water, right?
Yeah.
So they need to find, they could ship it in, right? But that becomes expensive because it costs diesel to ship it. Then they try to find water wells. They're not allowed to take the drinkable water in West Texas because we have a drought, people will need water. So they have to find large pockets of bag quality drinking water. They don't want it to be completely saline because it messes with the fracking process.
Mm-hmm.
But it can't be the quality that you can drink. So they need to find this, they need to find wells that are, hundreds of gallons per minute. Because, it would take you a week to pump out at 100 gallons per minute if you need 1 million.
Mm-hmm.
That
Wow.
would be essentially, 600,000 minutes of pumping to get that amount of water just for this on the small end. But, yeah. So in this case, this is a very small one, but we were looking for pollution in this case. So here I'm just going to choose this cross borehole setting. It optimizes the computation for this borehole application. Alright, and yeah, there we go. This one's quite small, so it goes pretty quick. Yeah, so of course we can look in dynamic slices, or we can just go directly to this inverted resistivity model. Come here, I know what the target is actually. So, okay, it's still not close enough. Let's remove some more of this stuff here. Right here, maybe. Yeah, so you have these patches in the ground of pollution. You can drill down and actually suck it out.
What was the pollution from?
This one, I don't remember what this is. Most likely it's typically when it's pollution, it's some kind of carcinogen called a DNAPL, and the chemical formula of this class, of this family, is called chlorinated solvents.
Mm-hmm.
We use them in degreasing airplanes. We use them in dry cleaning. We use them in preparing treated wood, like telephone poles. That's called creosote.
Mm-hmm.
So they're all carcinogenic, so that they have the ability of altering your genes and creating cancer.
Mm.
And so it's a type of pollution that's very difficult to get to because it's kind of opposite of amber, right? It doesn't want to float to the top, it wants to sink. It's denser. DNAPL stands for dense non-aqueous phase liquid. And what that means is that it's denser than water. But it's not that dense. But it's dense enough that if you have a hole in an impermeable membrane in an aquifer, it will go down and it can travel with the groundwater and then go up again. And it does these crazy things. And of course, if you drill a hole, you don't want to puncture a impermeable membrane because you might actually now pollute the groundwaters underneath it.
Mm-hmm.
So it's a very expensive problem, and these type of sites usually become what's called a Superfund site, where the government will spend billions of dollars to remediate. And what they do is they try to figure out this plume from wherever it came. If it was an Air Force base where they're degreasing and just washing it down the water, that's what they used to do. But we didn't know better at that. 30 years ago we didn't know better.
Mm-hmm.
But now we do. So then there's always like neighborhoods around these Air Force bases, right? So now the plume travels and migrates up and comes up in people's basements, causes a higher rate of cancer. It's all completely correlated with these plumes. And the problem is that DNAPL doesn't flow like a plume like we classically thought. What happens is that they'll put wells here, which they pump, and they bring it up to a piece of machinery that refines it, and it pumps the clean water back down and it washes the system through.
Hmm.
But the problem is that if it's not flowing in the aquifer correctly, then you're never going to capture it all. So what they found with their equipment is they could actually localize and say, I could drill here, but if I drilled 1 meter in any other direction, I could not get it. But I could drill it here and get several meters of free product, and you suck it up. And then once you suck it out, then microbes in the ground will actually just eat the rest of it.
Hmm.
Yeah.
Pretty amazing.
Yeah. Maybe we should just stop here and go for some lunch.
Sure.
So I've essentially showed you pretty much everything.